I see a lot of familiar faces. So who here was not in computer club before today? Raise your hand. Okay, a few people. Mostly computer clubbers though. All right, cool. All right, so the talk today is defining, executing, visualizing quantum circuits using the Qiskit SDK. It's going to require a little bit of background information on quantum computing, but it's a hackathon, so I assume you're actually working on something at the same time. So we're going to skip basically all the matrix math and most of the probability. So you can think of this as the ELI 5 for quantum. Hopefully it's enough to make everything make sense, but not enough to make your eyes cross during this. All right, so who am I? Ooh, going too far. Strong. I got my Bachelor's of Arts in CS 2017 at Western. Currently working at IBM. I've worked there both on quantum, cloud software, OSS, also master inventor there. If you have heard any of my container ramblings, you already know. I also like to play and make games, so if you're in fighting games, DM me. And presentation, thoughts are mine, etc. It's not a company thing. All right, so step one, what is quantum computing? And really it's just all probabilities. Forgive my one meme and the matrix math, which we'll gloss over. So first of all, this stuff is super duper cold. You need to have superconducting temperatures, so you're not going to end up with a quantum computer in your house anytime soon, barring room temperature superconducting, which as we know is also not room temperature, but we'll see. If anybody is on the PhD physics side of things, maybe you've already heard about who prepares quantum tunneling, superpositioning, entanglement. Really all you need to know is that instead of bits, we have qubits. It's just a quantum bit. It has a little bit more information stored in it, and that's a representation on the right there, the block sphere. You can think of this as the basic unit. So instead of 1 or 0, you're sort of representing a point on the sphere somewhere. All right, so with classical computing, your standard bit, generally speaking, 1 or 0. I believe there was some early, red curtain era computing that had more than 0 and 1, but we like digital here mostly. However, classical is not quantum, and quantum has a whole lot more than 0 or 1. So for the superposition diagram there on the left, well, this sphere is showing up very well, but it is a sphere, and you can think of 0 as being the North Pole, and 1 as being the South Pole. However, in quantum computing, you also have all the other possible positions on the front of that sphere. So, point being, you can represent a lot of information with 1 qubit, which is why it's really good for probability and matrix math. All right, so brief ELI 5 about quantum computing. So why would we be interested in this in the first place? After all, we've been working on classical computing for many years. We have supercomputers. Why would you use it? Well, partially because of this nice Venn diagram. So there are some problems that we can't figure out currently or figure out in a timely manner. And on the right side, we have some that we can address with quantum and classical. But in the middle, that's sort of where we are now. So we only have a subset of all the problems that we would like to be able to do today classically. So what sort of example can I give of potential problem areas? First one is molecular simulations. If you're doing material science, this is really big for that. Traveling salesperson, I think everybody's heard of that. If you're in comp sci, think of that as FedEx delivery most efficient type thing. And then factoring large numbers is also quite important. In this case, that'd be cryptography. Quick show of hands, who's heard of quantum cryptography? Post-quantum cryptography? You guys have all watched the Veritasium video? Okay, cool. But the idea is that with many of these domains, we can reduce the standard big O sort of plot to hopefully something that's better. In a lot of these cases, you get beyond like 4 or 5 inputs, and suddenly it's into the a bajillion. But yeah, hopefully you can convert some of these to linear or constant time. Best known example probably currently is Shor's algorithm, which you may need to be concerned about, but not really. The idea is same thing. More efficient, checking a vast number of outputs at the same time because of the block scale we talked about. All right, so how do you actually program a quantum computer? Well, that depends on what you mean by programming. As you have seen in Space Dog's talk, there is plenty of assembly going on, and there is some assembly-like version for quantum. But most software engineers, A, not big on assembly, and also don't have a PhD in quantum physics. So how do we merge these two? Because we want software engineers who can work on quantum computers who also don't have to take 8 years to get a PhD in quantum mechanics. So many companies, including mine, have created some open source software to work on quantum computing. The idea is that we have a compiler that already exists for a variety of backends. It's supposed to be backend agnostic. It's pseudo backend agnostic technically because of the difference between different types of quantum computers, so it's not going to work for a quantum annealing machine. But Qiskit is currently the most popular framework, so I recommend checking it out. And it comes, as you might expect, with a bunch of tools that any good library would bring. So it has a bunch of quantum algorithms built in, has some applications for machine learning, nature, finance, standard optimization problems, and simulating quantum hardware. So the neat thing is you can simulate what it would look like, well, for small amounts anyway, what it would look like on quantum hardware before you actually run it on quantum hardware. So you might be familiar with something like this. It's pretty similar to the way that you would do it with standard classical computing. So you're going to build your program first, or in this case, a circuit. Transpile, technically not compile, because we are changing our, in this case, Python input into some version of whatever backend quantum computer is going to use. You're going to run it, and you're going to check the output. So, how we actually build a quantum circuit. For ease of use, let's compare this to classical computing. So classical computing, you have bits, binary circuits, logic gates. I think most people are familiar with the logic diagram on the right. Show of hands if you're not. Everybody seen it? Great. So let's use this analogy then. So qubits in this case are represented as wires, pretty much the same as you would have the bits in the previous logic diagram. And what's slightly different is that gates represent operations on the same qubit. So whereas in classical computing, you would generally have like a XOR gate or an AND gate or something, and you get one output, you may end up having the same amount, or you always have the same amount of qubits out as you do in. And then there are a bunch of operations you can perform. It's domain specific, but we'll get to that. So for our basic intro here, we have some Python. It's in Courier, it's in Python, so under the headings there. So you just want to make a circuit that has 3 qubits. It could be any number you want, but you are going to run into problems where there aren't very large quantum computers yet. We're getting there. We're in the hundreds. Not quite thousands, I don't think. Or wait, no, thousands are out, but you have to pay for them. That's the difference. You're going to add an H gate. In this case, that's a Hadamard gate. If you're interested in the PhD math, look at the bottom, ask me questions later. And then we're going to add a CX gate. You can think of this as XOR, but basically we're flipping some quantum bits. So it has a fancy visualizer, pretty simple. You just draw your circuit. This is the circuit we just made on the previous page. So you have your Hadamard gate and then 2 CX gates. As far as advanced stuff goes, there are plenty of things already using quantum for applications you might not expect. So the first one is that PyTorch has a QGAN implementation. So quick show of hands, who knows about GANs? All right, brief detour on GANs. GAN stands for Generative Adversarial Network. Okay, show of hands for machine learning. People heard about machine learning, right? Yes, grudgingly, okay. So the idea with a GAN is that you have 2 simultaneous machine learning algorithms, essentially. One that is trying to fool the other, and then you reverse them when they get too good. So the idea is that if you could fake paintings well enough, right, to fool like an art collector. You could make $1 bajillion by selling counterfeit art. And the idea is that once you can do that, then you switch which algorithm you're training to the other one, so that it recognizes, oh, actually, I know that the counterfeiter made this because I trained it, and then you can sort of go back and forth in your own personal arms race. Anyway, there are many complex applications that are already using quantum computing. Just a fancy visual aid, because I know we've mostly been in the math department so far. All right, so let's look at slightly more complex, but still within the visualizer here. So here you have your Hadamard gate, 3 CX gates, and then you're doing a poly on all of them and measuring them. So a little fancy symbol on the right there is measurement. And you can do a whole bunch of this. So if you want to rotate or invert or whatever, you can do all that. But again, trying to avoid the matrix math during this talk. So briefly on quantum hardware, we have also made a what you see is what you get tool. So again, quick show of hands, who has had to work with a PhD researcher? Not too many. Okay, I will tell you they're very picky. And they like to deal with things that they can draw on a whiteboard. They are not software engineers. We are software engineers. We like software. So when they come and they say, hey, I want to do X, Y, and Z, and we say, okay, you just have to type this in. Even in Python, sometimes you get people staring at you like, you're drawing a third head or something. So we've made a WYSIWYG tool, which hopefully works out. Yes, okay. So the idea here is that you can create the Python code by just drawing what you would on a whiteboard to represent standard quantum states. So right now we have 3 qubits on the left, 4 qubits, excuse me. Thrown in a Hadamard gate on the first one, CX gate on the second one, CX gate on the third one. This was a particular point of contention. So the thing that's being added in right now is a barrier, and essentially the problem was we had PhDs coming to us and saying, I put in the correct structure visually, and what I'm seeing is not what I put in. And we said, yes, because they're equivalent, but faster in the back end, because it's a compiler, that's what it does, it makes it more efficient, right? So as long as they're equivalent, we can do some fancy operations to make it faster. But they're mad about that, so we put in this block here. As long as you're blocking that, it won't change what it looks like to the person actually inputting it. But on the way back end, if you want to go super low level, it's doing a bunch of optimization tricks. So blocked off those, put in a measurement for qubit 1, qubit 2, qubit 3, and then run. And brief thing here is we do have free quantum computing resources. So if you want to actually run this circuit or a similar circuit or just dip your toes into it because it's coming whether we like it or not, you can go ahead and actually run some actual quantum circuits on quantum hardware. Not an advertisement. I guess the only downside is that there is a queue for a lot of this. There's a lot of, again, PhD researchers that are going to have to stand behind in line. But at the end of the day, pretty simple to queue it up. And you can see the code that it generated on the right. Hopefully that's visible somewhere over here. But it's doing all the things that we did when we constructed the gate there. All right, so what's next in quantum computing? If you want to learn more about this, you can DM me or hit some of these search terms up. But basically, there's a huge textbook that Qiskit put out that is sort of an intro to Quantum 101. There's also some tutorials around Qiskit in general, but if you understand Python and Python libraries, you're basically all the way there. I would highly recommend checking out the contributing section. I've had many people who have contributed now who know zero about quantum computing, or did when they started, but now can say, I worked on a quantum SDK. So would recommend if you have some free time. It's pretty cool. You get to rub shoulders with both the software engineers and the PhD guys, so best of both worlds. All right, we blitzed over it, hopefully enough that you guys can still work on your projects, but also get your toes wet in quantum. Do you have any questions other than where's the matrix math? Space dog.
You said the bleeding edge is 1,000 qubits, right?
I think it's slightly over that.
How close is that to like breaking RSA?
Not close.
Not?
What does breaking RSA mean?
One of the big deals about, well, maybe I should let the quantum computer explain.
You can answer it if you want, but yes, the problem partially is how many error correcting qubits you have versus how many actual qubits you have is a different thing currently. The idea is that you want, some of the stuff that you have in classical computing, like Hamming code nonsense, all that sort of stuff. But yes, the answer is it's not there yet. And the major problem that you're talking about is the sort of capture now and then read later. There's really no good way to stop that. However, we are putting in quantum safe algorithms now, which is how you're going to stop it going forward. So you can't stop, the data that you've leaked out in the last 20 years or whatever to whatever third world government might have a quantum computer that's quite large that they won't tell us about. But in the future, if you're using quantum safe cryptography, which is in most major packages now, I think there's a few outlying. I won't name names, but there's a quantum consortium now. It's being made. It's in, I think, all of the Linux tools, or at least close to. Maybe there's a few PRs open. But yeah, the idea is that going forward, as long as you're using those algorithms, which are slightly bigger, slightly slower, you won't be sort of leaking data in that way where you're sending it out now and then they can just decrypt it later. ACP.
So do those new algorithms, I guess I don't really know like what defines RSA. I'm assuming that is an algorithm or a standard. So everything that is encrypted with that, do we need to go, assuming quantum computers get to the point that they can like do this, do we need to go and re-encrypt everything? Like, are all of my SSH keys going to be burned in 20 years? Or, not that that's like really an issue, but you understand.
That is the fear, yes. The fear is that at some point in the future, we believe with certainty that this capability will be there. And
so start using the new algorithms now, so you don't have to redo
Yes,
it.
exactly. Use the new algorithm as soon as possible if you're worried about leaking what you have now. Otherwise, you're going to have to re-encrypt some things later, and or it's already out there in the wild, right? So if you put it on Facebook, it's already there. Sorry, somebody scraped that. Think of that with basically all of your data, right? So the things that online banking, paying your student loans, whatever, like all of that is essentially out in the open. If we can capture that now, we can find out the details about that later. So yes, that might be a bit scary, but hopefully, by the time it's there, right? Quantum cryptography has been in the wild for, say, a year-ish so far, but once it's integrated into everything, hopefully there's a few years before we actually break RSA and have a huge headache. But yes, good question. Anybody else? Sounds like that? All right. See some glaze over eyes. Hopefully that was simple enough. And again, apologies for no matrix math, or you're welcome, depending on which camp you're in.